Hello, my name is Robert Taylor. I'll be presenting my Stanford CS230 research project entitled Matryoshka Vision Transformer Compression. This is a project that looks at how to make vision transformers smaller using something known as the Matryoshka representation learning framework. And quite simply, what Matryoshka representation learning does is it takes a conventional objective function, such as what's used here for image classification, and it adds this inner summation. So you take, for example, like a cross-entry loss script L, apply it to the output of a network represented by F, parameterized by theta and Z with an input X and a label Y. And if we assume that we have a set of weights C sub M and a set of nesting dimensions, script M that can vary, in this case, from 8 up to 512 exponentially, that satisfy this nested structure constraint, as I'm showing here, then we basically just learn a set of models. In this case, 7 models are jointly learned that have this embedding dimension structure that's enforced. But other than that, the objective function is the same as any other image classification objective would look. The general architecture from the first vision transformer from 2020 from the Google research team, I apply a couple modifications. I use dual patch norm on the embeddings, and I allow those embedding matrices to be nested to basically reduce the number of columns in E, which will reduce the number of dimensions of Z, and Z is the embedding dimension which gets passed through the entire transformer model. So if you can reduce Z, it will actually compress the entire transformer encoder backbone as well as the MLP head that's used for classification. Secondly, I also use a fixed absolute positional embedding instead of a learned positional embedding. Step 3 is I learn the Matryoshka objective, which is, as I mentioned before, is just the summation of an ensemble of models where the traditional cross-entry loss script L is used, but it's we're imposing a nested structure over the embedding dimension Z and then summing up the contributions from all those individual nested models. Step 4 is at the end, after you've done your validation or evaluation of the model, you can look at the top one accuracy as a function of the embedding dimension and basically just pick the embedding dimension that gives you the amount of compression you want. Is that just like with any other model, we start with a batch size B, we have our hyperparameters, we initialize the patch projection matrix, the backbone parameters of the transformer encoder, and the MLP classification head. And those are initialization can be done with Xavier, which is what I use in this paper. Then I start the iterations of the training loop where we sample a batch of images X, labels Y from our data set script D. We patchify that image, which is what tokenizes an image. We then start looping over the nesting dimensions. And for each one of those, we enforce the nested embedding structure on the patch embedding matrix E. We generate the corresponding positional encoding vectors. We apply the dual patch norm in step 17. And then I loop over the transformer blocks. So these transformer encoder blocks shown here represented in equation 18 through 20. The classification token is then fed into the multi-layer perceptron head to generate the y-hat, the estimate for the class label, and then that's fed into the cross-entropy loss. At dimension 512, you can see that for SciFar 10, I'm getting a 7% increase in performance, 9% increase on SciFar 100, and then also, as I showed earlier, even going all the way down to 128 dimensions, the performance now, the dimension size dropped by 4. The parameter count drops by 16 because it's a quadratic. And so even with 16x, we're doing just slightly worse than the baseline model. At 4x reduction, we're actually still outperforming the baseline model. So this